Okay, so we've learned Fubini theorem. Yeah. Yeah, complete. And like notes with like annotations I make here are under like the Monday or Wednesday one. Okay, so Fubini's theorem for double integral in polar coordinates. So now we're changing coordinates, right? So over this is, I think this was erased for some reason. But basically for Fubini's theorem, for double integrals in polar, the only difference now is that our expression, we want to rewrite it in terms of r and theta, and then we want this extra r here. So dA equals r dr d theta, and don't forget the r. If you're, how you find the limits of integration. So let's do an example real quick. So we have set up the limits of integration for this double integral for polar coordinates in polar coordinates. And R, or our region, in the xy plane is given by this expression. So R is greater than equal to 1. Remember what R is in cylindrical coordinates, or sorry, in polar coordinates. R is x squared, or square root of x squared plus y squared. So for your lower bound, you have a circle, which is the green circle. The upper bound, this 1 plus cosine theta, is this weird orange shape. And so your region is, it has to be, yeah.
Like, are we expected to know the shape of the 1 plus cos?
Probably not. I think 1 plus cosine theta is probably a weird shape that you wouldn't have to like draw.
Oh, so they would give it to us like that.
They probably wouldn't, maybe, yeah. Or they wouldn't like give this question at all. It'd be like a better expression. But this is just a common example from like Calc PC or Calc AB with the shape. So this is your region, which is highlighted here. And so for your bounds, you want to first look at, this is in the XY plane. First look at your R bounds. So in my like how to find the limits, the first step, imagine a ray cutting through your region in the direction of increasing R, meaning radially outward. So you always start inside. So you always start inside and draw a line radially outward. Your curve enters at this green point. That is R equals 1. And it enters at this curve, which is the 1 plus cosine theta curve. Then looking at your region, out of all these possible lines we can draw, what are the bounds or the min and max for theta? Well, theta goes between negative pi over 2 to pi over 2. Because it's this entire highlighted region, so it's the entire right-hand side of our graph. So theta is negative pi over 2 to pi over 2. Any questions on how I found the bounds with that? Okay, so then we have formulas for converting Cartesian integrals to polar integrals. So the common ones you should know are x is r cosine theta, y is r sine theta. And this I just mentioned, dA is r dr d theta. So when you're converting from Cartesian to polar, don't forget the r. Okay, let's actually, okay. So if you were asked to compute this expression here in polar coordinates, there's 3 steps you need to do. First step is, so rewrite your bounds. Bounds. Second, rewrite your expression. And third, rewrite your differential, or in this case, it's our dA. So we have this shape here, our region, and we want to find the bounds for R. So R goes from, oops, sorry. Okay, first we want to draw this, what this is in our like regular coordinates. X squared plus y squared is our circle. Our bounds are going from y from 0 to this upper circle part. So we have this top part now, and then x is going from 0 to 1. So we don't have this left-hand highlighted part. So just the highlighted part is our current region. If we want to rewrite it in polar coordinates, r goes from 0 to the exiting point is that circle. That circle is r equals 1. Then theta, you just think of a unit circle. What are our theta? It goes from 0 to pi over 2. 0 to pi over 2. So we rewrote our bounds. Now we want to rewrite our expression. What is x squared plus y squared in polar coordinates? Well, based on our conversions, this is going to be r squared. And then this differential, we can rewrite it as r dr beta. And so that would be your integral, and you can keep simplifying or evaluating it. And you'll see that evaluating this is much easier than evaluating this first line, because the first line of x and y, then you have a square root plugging in, which is more messier. So we want to look at our region, and you look at your picture, think about a unit circle. If your angle here is 0, pi over 2, pi, and 3 pi over 2, our region is just from 0 to pi over 2. Any other questions on this before I move on to cylindrical coordinates? Yes.
What are the bounds of theta for the previous example?
Yep. So theta, think about this is just a flat unit circle. This is our pi over 2 angle, and this is our negative pi over 2 angle. Our entire region is on this half of the plane.
Oh,
So anything between these theta bounds, our region is between. So if our region, say our region was 3/4 of a circle, then our theta bounds would be from negative pi over 2 to pi. Now let's move on to triple integrals. Okay, so triple, yeah.
Cylindrical coordinates are the same as polar.
Cylindrical is in 3D, polar is in 2D.
Oh,
So that's the only difference. And you'll see in polar coordinates, we have a drd theta, but in cylindrical, we add a dz drd theta. Okay, so for triple integrals, we have two types, cylindrical or spherical, as you've all probably seen already. Some common conversions, so cylindrical to rectangular, rectangular to cylindrical. These are just some formulas. Okay. So Fubini's theorem for triple integrals in cylindrical coordinates. So when you're converting to cylindrical coordinates, dv, we always think of dv as dc dx dy, right? Where dx dy is dA. But in this case, when we're converting, so think about converting this dA part to polar, we'd have an r drd theta. So for cylindrical coordinates, also don't forget this r. So in this case, it's very easy to forget the r because you just do dv drd theta. But don't forget the r.
forgotten over there, right?
Where?
Like when it says then, example.
Then this is just the formula. So if you have a triple integral of some function dv and you wanted to convert it to cylindrical coordinates,
Yeah.
they equal to this. Where
But you forgot the R, right? Over there, like
oh, I see. Yeah, there should be. Thank you. Okay, any questions on the definition? Okay, let me do an example. So we have find the limits of integration over this region in cylindrical coordinates. And our region is given by this. So it's bounded below by a plane, laterally by a circular cylinder. So that means bounded on its side by the cylinder, and above by a paraboloid. So for this, we like you don't necessarily need a picture. So, but let me just imagine what it looks like. So we have some paraboloid bounded above. We don't care if it looks like I don't know if it looks like that or if it looks like that. But the point is that we have a cylinder and we're bounded above by some paraboloid. So it's gonna like stop halfway. So our region is gonna be this bottom part of our cylinder and the part that is also above our z-axis. So for z, we know that z, if we draw lines in increasing z direction, we have to enter the xy plane first. So we enter z equals 0. Then we exit at this paraboloid part because we said that it's bounded above by the paraboloid. What is z equals x squared plus y squared written in polar or cylindrical coordinates? Well, that's z equals r squared is our paraboloid. So our bounds for z are 0 to r squared. Next step, we collapse the z-axis, and what are we left with? Well, you can imagine that you're left with this like cylinder part. So think about the shadow, and in the xy plane, you're just left, yes. Oh, yeah.
Yeah, I have a question about like this is above out of tabloid.
Mhm.
Is it like are we not supposed to know how to like graph it as long as we just know that's the top row?
If you want to know how to graph it, that might be helpful. But like I'm saying, like if we didn't know how to graph it, we can just visualize that like no matter what, the paraboloid is on top. So we can use that our upper bound for z as that paraboloid. But if you knew how to graph it, that also would be helpful. Okay, so for r, we have this thing in the xy plane now. For r, remember we draw lines radially outward. So we start inside, so r goes from 0, we go outward, it exits this circular curve. And what is that circle? Well, that's our radius of our circle. The radius of our circle should be 2 because our cylinder was given by x squared plus y squared equals 4. So square root of 4 is 2. Then for our theta bounds, well, we're not limited by theta. We have a full revolution of our shape. So theta is 0 to 2 pi. So when we write it, we have this theta bound, r bound, d bound, and we have dz, r, dr, d theta. Any questions on that? This example? Yep.
For the like DZ or DR data,
Mhm.
do you guys rearrange that? Really have that that's like yeah, it's like R DC DR data.
Yeah, that's fine. Okay. Any questions before I move on to spherical coordinates? Okay, let's do some spherical coordinates. So again, I have formulas for you guys. So spherical to rectangular or rectangular to spherical.
You don't have to memorize them, right? That's what Brimmer said.
Oh, you
It's for
said,
spherical.
okay. Yeah, if he said you don't have to memorize them, then you don't have to memorize them.
It said on the study guide that was like you don't need to memorize the conclusion, but maybe that's specifically.
Probably like maybe he wouldn't give you like a random like obscure like this. Like you'd somehow need to know this formula probably. But I think no matter what you'll see a little bit later, you should know that converting to spherical, like just memorize that you have this rho squared sine phi 0 d phi d theta. Yeah, I think this one you should definitely memorize regardless of what anyone said. And you should also memorize this one for the cylindrical. Okay. And you also have conversions for spherical and cylindrical to spherical. I just thought I'd include them here in case. But I don't think they're used that often. Yep.
Why is it not y or x? Because isn't theta dependent on the xy plane? And polar is an x and y. And if theta is theta, then it should be just like-
I think where the formula is given it
like,
might be X, but
In the video, it did say,
V.
yeah, but I don't.
yeah, well, why is theta?
Sine of so inverse tangent would be cosine y over z sine y over z, and y is rho sine phi sine theta, z is rho cosine phi sine of, so I'm plugging in our conversions. Okay, and then we get cosine of the rows cancel out. This is tangent phi sine theta. Sine of tangent phi sine theta. Let's see. Theta. So right now we're claiming theta equals this. And we see that this is inverse tangent of sine theta. Okay, I'm not too sure about the derivation. This might take a little bit longer.
That's fine. I was just wondering, because I thought it was y over x, because if you're gonna be basing theta off of the xy plane, and in the past I've always heard it as inverse tangent.
Inverse tangent of y over x, that might be for polar coordinates,
Yeah, so my question was,
but now we're in 3D, so it might be slightly different.
okay, because
Yeah.
the way you wrote it is that theta is equal to theta down there, like converting from cylindrical to spherical. And if that's the case, then like y is not y over x if it's the same thing. And like in cylindrical, c is c, and theta is based entirely off of the x, y, y. So shouldn't it definitely be inverse tangent of y over x? If that's the case, then why would it not also be the same thing as spherical? We don't have to spend more time on this. I would just.
I think just because there's like an extra like added dimension, so now there might be like a theta in, like now you're thinking of theta in 3 dimensions instead of just like a flat 2D surface.
But isn't C looking at C and theta looking at x?
Yes, but that's just a tool for us to determine like our limits. Like our tool, the reason like we collapse the z-axis and just look at the xy plane for theta, just so that we can like think about how to find the bounds. But there might be still like theta in 3 dimensions, I think.
I think in my notes, like according to the Clarice videos, they had arismus or whatever, like the theta we have here on the second one. On my notes it says arctan 1 over x.
Yeah, mine
Yeah,
too.
so
Y over x.
Yeah.
Oh, okay, so maybe my notes are wrong then. That might also be the case.
oh wait, no, I meant the set because you wrote it different that compared to the videos. Like they had B as the third one and the theta as the second one.
Oh, like
It
flip.
doesn't- Like they said in the video, it doesn't matter which
Like
one.
that.
Like, yeah, and they had arctan y over x for the theta and arctan r over z for.
Yeah. Okay, that makes more sense because phi I think is based off of like the up and down.
Mhm.
So that
Okay.
makes sense.
Yeah, I may have just copied it wrong. So whatever it says in the video. Okay. Okay, so let's do an example. So if we are trying to find a spherical coordinate for the equation of this cone. So think about it for a bit. And how do you guys think we should convert this so that it's a spherical equation instead? Any ideas? Yeah.
Be the R cosine, R sine coordinate.
R cosine, that's for polar coordinates. So we can't use polar coordinates in spherical coordinates. Yep. So we should probably want to use like these. So let me copy them over here. And so we know that z equals square root of x squared plus y squared. In our normal coordinate plane, this is a cone. What if we plug in z? So we substitute rho cosine phi for z, and we substitute x sine phi cosine squared plus, and we also substitute y. So y is rho sine phi sine theta squared. When we have a cosine squared and a sine squared, this would end up being simplifying to 1. So you're just left with rho squared sine squared phi or rho sine phi. So right now we have rho cosine phi equals sine phi. So we have 1 equals, if we divide both sides by cosine, we have tangent phi. Tangent of like some angle only equals 1 when phi equals pi over 4, for example. So we see that if phi equals some constant, this is also the equation of a cone. So if you ever see like phi equals something, you know that's a cone. If you see z equals this square root x squared plus y squared, you know that's also a cone. Any questions on, yeah?
So if E equals any angle, it's a cone regardless of.
Yes, if phi equals any constant, so any number.
Okay.
Yes.
What will the constant tell us about the cone?
So for example, for phi equals pi over 4, that would mean that like when you're doing phi, when you're finding the phi bounds, we always see what is the angle phi makes or some ray makes with the positive z-axis. So phi being pi over 4 means that this angle here is pi over 4. So the largest angle that like your shape, any point on your shape would make with the z-axis is pi over 4. So this is like pi over 4, yes. So the angle is pi over 4. Any questions on that? Okay, and I did right here. So for example, like if phi is some constant, it's a single cone. If rho is a sphere, that's a, oh, sorry, if rho is a constant, that's a sphere. If theta is a constant, that will end up giving you a half plane. Okay, and then now we have Houdini's theorem for triple integrals in spherical coordinates.
What do you mean by a half plane?
Just like, so a half plane is, it contains the z-axis and makes some angle with the x-axis. So like, it would just be this half plane instead of like a full plane. I guess. Okay. So why don't we do an example for spherical coordinates? Okay, let's do this example. So it says find the limits of integration over d in spherical coordinates where d is bounded below by some cone. Here you see phi equals some constant again, and above by the sphere. So here you see rho equals some constant. Okay, take like a minute to think about what bounds should we be using for this question, or even just draw the shape first. Okay. Yeah. So the phi angle, so phi equals pi/4 means that the largest angle that any ray on our shape makes with the z-axis is pi/4.
Okay.
Okay, so like, for example, first let's draw this. So phi equals pi/3. That's gonna be some, we know it's a cone. So it's some cone, and then it's bounded above by the sphere. So we have some sphere here. That's a, okay. So what should my bounds for rho be? So rho, I always have these like how to find bound like descriptions. Rho, you want to imagine a line cutting through your region in the direction of increasing rho. And you want to, yeah.
How do we know it's bound, that it's centered at your?
Because we saw that, so we saw above here that p equals pi/4 was equal to this equation, right? And if you graph z equals square root x squared plus y squared, it's centered at the origin. Yep. Okay, so what should my rho bounds be? What do people think? Yes. So rho goes from 0 to 1 because you're drawing a line in the increasing rho direction. You enter at the origin, that's rho equals 0. You exit at the sphere, and the sphere is rho equals 1. So rho goes from 0 to 1. Yes.
So the fact that the cone is kind of, as it gets bigger, is like cutting off some of that space doesn't matter. If, for example, if it was inside, there was another sphere inside the cone, and that sphere had a radius of like 0.5, would rho be going from 0.5 to 1?
So if you had like a smaller sphere inside a bigger sphere,
Yeah.
and your region was like this,
Yeah.
then yes, it'd be going from this point to that.
Okay, so over here, I know that like at a certain, like it's kind of like the full thing from the origin to the end, but like, do we not have to account for the fact that it's taking up space? Like, like if you move up, right, and some of the radius is no longer.
Oh, like the fact that this is not touching?
Or like it's kind of like you're taking out space, right? So like with the radius.
Well, the space is, so you're bounded, this is our space. So you just imagine this pizza, you enter at 0 and you exit at the crust of the pizza, which is our sphere.
Oh, okay, I see. So if we're finding the cone, then we're going from where it took the cone to the end.
Because this is just our region. Our region is not including like this sphere part.
Okay, and if we just had a cone, it would also just be like the full length of the cone's row.
Yes.
Okay.
Yeah.
Sorry, can you explain how it was one? Like at what point is one?
So rho is 1 because you want to find where does your ray exit. So we're drawing a line starting at the origin and we're going upwards. So we enter at rho equals 0 and we exit at the sphere. The sphere, they gave us the equation of the sphere is rho equals 1. So that's why the exiting point is rho equal 1. Yep, and you can also, yeah, sphere is rho equals 1. Okay, then for phi, so phi, you always want to look at, you draw a ray and look at the angle between that ray and the positive z-axis. So like this line would be equals, C equals 0, because that's like equal to the z-axis. Imagine it's on there. If we head up to this line, this is c equals pi over 2. This line would be c equals pi. So the smallest phi we can have is 0, even though it goes to the left of our z-axis. Remember, angle is, what is the angle to the z-axis? So even like this part, like negative pi over 3, like just start at 0, because negative pi over 3 is like a larger number. So we start at 0, and then we want to see our region. If we draw any ray in our region, this might be like p is like pi over 6 or something. But the last ray we can draw is this exact line of our cone. And what was that line of our cone? What did we say it was? Well, our cone was given by pi over 3. So the last one is pi over 3, because that's this angle here. Yeah.
If we had a sphere and it was like just the way it was placed, it was always above z equals, like the z squared equals 0. Like it just happened to not go in that big of space at all. Would we have our 0 to pi over 2?
Yeah.
Okay.
Yes.
A question. So the sphere is supposed to be like the top of the top half of the sphere is supposed to be but like in the positive axis, like
Yeah.
how it's going,
Yeah, I didn't draw it that accurately. Yeah.
Yeah.
Yeah, sorry. I was focusing on this part, so I didn't make it bigger. But yeah. Okay. And then finally, for theta, we imagined collapsing the z-axis. Well, you have a sphere, you have this like circular cone part. Imagine looking downwards in the xy plane, you'd just be left with the circle. So that's a full revolution, no limits on theta or anything. So theta is from 0 to 2 pi. Any yeah.
We use spherical coordinates here. Would that be like when it comes to like cones, is it just better to use spherical coordinates?
Yeah, because cones are usually like phi equals a number, and phi is only in spherical.
Even if they give it to us like like
You can do it in cylindrical.
Yeah.
Maybe spherical might be easier sometimes.
Oh, okay. So like when we choose whether to use cylindrical or spherical, like I guess how do we know what's best in each case?
So I think if you have anything with spheres or cones, if you have spheres, definitely use spherical. Cones, I would also say spherical, but it also depends on what things you're given. Like if the things you're given are in cylindrical, then that might be assigned to use cylindrical, because otherwise you'd have to do conversions to get to spherical.
Yeah. Okay.
So yeah, it depends on like what they give you.
Could phi be negative pi over 3 for the other side of the cone?
But negative pi over 3, that's like in absolute value, that's equal to pi over 3. So you want to see what is the smallest angle you can make with the z-axis. The smallest angle is still 0. Like negative pi over 3 as an angle, that's still like a large angle. So our lower bound is still 0. Yeah.
I think the way Rilla described it was that like with all you do is worry about like how long it is, and then the fact that theta goes from 0 to 2 pi kind of covers the other side, and like what we think goes the negative pi.
Yeah, you can think of it that way. Yeah. So for phi, always start at 0 and see what your region goes to. Okay. Grace mentioned that you guys should remember how to do probability stuff. So like finding C. Yeah. So like if you're given some domain and we wanted to make sure that this was a probability density function, From last week, we know that we took the triple integral or double integral of our function and set it equal to 1. Now we have a trick where that triple integral or double integral, we can compute much easier because we can rewrite it in spherical coordinates. So if we were given this domain and our function, we want to do a triple integral of f equal to 1. So think about our bounds and any suggestions for the bounds of our triple integral. Or first, let's just draw our shape first. X squared plus y squared plus z squared less than or equal to 4, that's a sphere. X is greater than 0. Y is greater than 0, but there's no restrictions on z. Z can be anything. So what like part of our sphere should I shade? Should I shade the top half, the bottom half, the right half, the left half?
One looking
Towards us? Like this? Kind of?
Yeah.
Yes. So x and y have to be greater than 0. So I should have labeled my axes. So it should be on like this side. And then z can be anything. So z could be all the way up here or all the way down here. So we kind of have, you can think of it as like a slice of an orange is our region. So for our z bounds now, or sorry, row bounds, because we're doing this in spherical. So row should be going from, if you enter here, row goes from 0 and you draw radially outwards. Well, it goes to that sphere. What is the sphere equation? Remember that row equals square root x squared plus y squared plus z squared. That's a formula. So our row e squared equals 4, or row equals 2. So row goes from 0 to positive 2. What does phi go from? Well, we said that z can be positive or negative. So imagine phi with the positive z-axis, that's 0. So phi goes from 0, and you can go all the way to the bottom. So it's pi, because you could go all the way like 180 degrees. For theta, you have to collapse the z-axis, and so you're left with the positive xy plane. So remember, when we have a sphere, we collapse, we're left with a circle. The only limit we had for x's and y's is that x had to be greater than 0, y greater than 0. So our region in the xy plane is this quarter part of our circle. So our theta bounds are from 0 to pi over 2, because 0 and pi over 2. Yes.
Are the lower bounds for row always 0?
Not necessarily, but most of the time, yeah, they start with 0. But like this question that Ananya suggested, row would start at this other sphere, not at 0. Okay, and so you would have in total, when you rewrite your like expression, we found the new bounds. This was our probability density function. We have to make sure that we rewrite this in spherical coordinates. So this is c times rho squared, because rho is square root of this. And then for dv, what should I put for dv? Yeah.
Oh, sorry. I have a question regarding the bounds.
Yeah.
Can you teach me again how you found the bounds?
So what bound? Phi?
Yeah.
Phi, so phi is, you can draw any ray, and what's the smallest angle it makes with the z-axis? The smallest angle is 0. What is the largest angle you could make? Well, you could draw a ray down here, this purple one. That angle is directly 180 degrees below the z-axis. So the upper bound for phi is pi, because you go from 0 to pi. Remember, I said this is 0. If it went up to this point, it'd be pi over 2. If it went all the way down here, it'd be pi.
And and we can go with pi because it's x is greater than.
Because we don't have any limits on z. Z could be anything. It could be positive or negative. If they added another restriction that z had to be greater than 0, like they added that, then you would just have 0 to pi over 2, because you just have this top part. But right now z can be anything, so you want to go to pi. Yep. Okay. And so dv, when we're converting to spherical, don't forget that you have this extra rho squared sine phi and then the differentials. Any questions on this problem?
Can I see?
I want you to think about the next question, which will be like, out of these 3 variables, x, y, and z, which one might have an expected value of 0? So which one could have an expected value of 0? Thinking about our shape.
Can you go back to
The question?
no, to the answer.
Oh, yeah. So think about the shape. Which one? So remember, expected value is like kind of like an average. So which one might have an average of 0? Any ideas? Yeah. Yep, z-axis would have the expected value of 0. That's because x can be positive, y can be positive, then your expected value for x and y will probably be positive. But z has values that are positive and negative, so its average is around 0. Okay. And okay, this question, like question 23 is actually like the same idea.
Do you think we need to know how to calculate expected value and variance? Like, I know there's questions direct from the
I would know the formula, maybe. Like, I don't know if it's going to show up, but it might be helpful. And then for this one, this is as like, if z is less than or equal to 0, then that would be like your bottom half of the sphere. So b would be from pi over 2 to pi. Yeah. So just basically in this picture, if I had just shaded our bottom half, b would be from pi over 2 to pi. Okay, any questions on this problem before I move on to your variables? Yes.
Are we gonna do the surface area element in recitation?
Yeah, that's the very end. Okay, let's do, okay, let me summarize the main idea of, so the purpose of the change of variables theorem is that when we're doing our conversion to polar integrals or even spherical, so we just said that dv is rho squared sine phi, d rho d phi d theta. So why do we have this extra rho squared sine phi? Is because of our theorem. So that actually turns out to be the determinant of a Jacobian matrix, or the determinant of a derivative matrix. So specifically, think about in polar coordinates. If we're converting from r theta to xy, and we want to find the derivative matrix of this and take the determinant, you end up getting r. You could do the same thing for 3 dimensions. I won't calculate that though, that's a bit more. For spherical coordinates, you'll see that you get rho squared sine theta. This is just a note that sometimes you might have a variable, like if you have something as x equals something, y equals something with u's and v's, y equals something with u's and v's, it might be easier to find this derivative matrix because you already have your output as x and y, and you just take the derivative. But say you wanted to find this, but you were actually instead you were given u equals something with x's and y's. U equals something with x's and y's. Sometimes it might be, in this case, it would be much easier. Oh. compute this Jacobian matrix because you already have your outputs written and you just take each one, the derivative of each one with respect to x and y. So you can compute this first and take the inverse of it. Yeah, is the point of this thing. So if you are given two equations, like u equals something, v equals something, well, computing this determinant matrix, it makes more sense because you just take your first thing and you write it as u with respect to x, u with respect to y, v with respect to x, or v with respect to y. Like we can compute that, but the question might ask you to actually find this. So instead you can do that, sure, and then take the inverse of it to find what you actually need. Okay. Now, what is our change of variables theorem? So this is our change of, okay. Okay, I'll just go over here. So this is our change of variables theorem. It just says that if you're trying to take the integral of f with respect to like dx1, dx2, etc., then you can rewrite it, changing variables as f of some other values. So like this might be your r, this might be your theta. You take the Jacobian matrix, so this might be x, this might be x, this might be y. You take the Jacobian matrix or the derivative theta, and you write dr d theta. So this is just your general formula. And so applying that to our, like why it works, we see that the Jacobian matrix for the polar coordinates is r. We saw that, and so the change of variables theorem tells us that we can rewrite x dx dy as r dr d theta. Okay, let's do an example. Okay, take a minute to read this question and think about how we should approach it. Okay, does anyone have any ideas? First, let's like draw what it even looks like. Okay, so first, y equals, actually I'll just do it on here. Y equals natural log x is this curve here, the green curve. Y equals 2 plus natural log x is the same curve, just shifted upwards. So e to the negative x is this purple curve. And then 1 plus e to the negative x is this curve. So our area right now is this shaded region, highlighted region. So the goal of this question is we want to choose some u and v. The goal of change of variables is that we want to choose some u so that we can write u between two numbers and v are bounds between two numbers. Because then that will make doing integrals and like definite integrals much easier. Let's just write down what we have. In the green, we have that y is greater than equal to natural log x based on the picture and less than the orange one. So less than 2 plus natural log x. And I said the goal is we want to get something between two numbers. Yeah.
Why are you putting the natural x's?
So first they tell us that our domain is cut out by 4 graphs.
Yeah.
So we drew the 4 graphs, we have this region. This region, well, if you think about drawing a line in the increasing y direction, you go first through the green one, which is natural log x,
Yeah.
and go through the orange. Like the orange one is your upper bound version of.
That's not gonna make, right?
Yeah, it doesn't match it exactly, but you want to find, like, we see that these first 2 lines are similar because they both have natural logs in them, and we want to somehow compare them. Yeah.
You have done like either variable, either set of equations. When you said that like y is bounded by the purple line at the bottom and the blue line at the top.
Yes, so that's the next
Oh,
step. So the first step is we see something similar between the green and orange. So let's try to relate green and orange. We have green, orange, subtract by natural log on both sides. So y minus natural log x. You have 0 on the left side and 2. So now we have some expression. Let's name this v. V is now between 0 and 2. So we just found what we should choose for v. As someone suggested, we should also relate the blue and the purple. So the purple, y is greater than e to the negative x, and blue one is 1 plus e to the negative x. If we subtract both sides by e to the negative x, we get y minus e to the negative x. On the left side, we're left with 0. On the right side, we have 1. And we can call this our u. So we've just chosen what our u and v should be. U should be y minus e to the negative x. V should be y minus natural log x. Any questions on how I chose those bounds? Okay, and then the next question would be like, how do you relate x, y, dx, dy, and du, dv? So how do you relate x, y, x, dx?
Is that y or x?
Where? Here?
Oh, there. E to the minus x is smaller than y.
E to the negative x is
Yeah.
smaller.
Would that be y or x? That one.
Y. Because our equation is y equals e to the negative x.
Oh, yeah.
So we're relating these 2 equations, which says that y is greater than or equal to this one, and y is less than this one. Okay, so the next question would be like, what is the relationship between dx dy and du dv? That would be using the change of variables theorem. So change of variables theorem would say du dv equals the Jacobian, or the determinant of our derivative matrix, dx dy. How I kind of remember if like u and v is on the top or x and y is on the top is that whatever's on the left side should match my top, and whatever's on the right side should match my bottom. Okay, and then you can compute that determinant, and you would see that du dv equals this. Any questions on that? Yes.
What is the goal of when you got into the matrix?
Yeah, so we said that u equals y minus e to the negative x, and v equals y minus natural log x. So let's bring that down here. Here. So this first term is the derivative of u with respect to x, the derivative of u with respect to v. So u, the derivative with respect to x, this negative brings it down, you're left with e to the negative x. For y, there's only a y here, so it's 1. And then down here, this is the derivative of v with respect to x, v with respect to y. And so we take that from here. Any other questions on this problem?
How does that turn into e to the negative x?
The determinant is this way, so e to the negative x
Oh, okay.
minus this. Okay, I have a 3D example for change of variables here, which
So then we would have, can you show the final integral?
oh, there was, oh, so you would integrate like your bound of some domain would be like u equals 0 to 1, v equals 0 to 2 of whatever function you're given times what we found. So this 1 over this. 1 over this du dv, because we found that dx dy equals this. Because we found here that du dv equals that,
Yeah.
but we want dx dy equals something du dv. So I divide both sides by this term.
Wait, so then can you show me?
Because originally,
So now this is in terms of x, so how would you, if the integrals in terms of
wait, du dv. Oh, wait, let me. Okay, I might be missing.
and then what's the
Sorry. F is some function that you've rewritten in u and v.
Okay, so yeah.
U
what would
and
you do
v.
with that?
Yeah, so maybe
And then this is like calculations.
there might I don't think so. So it just might not work. It might just not work for this question, I think. But usually you would have like u's and v's and it would work out.
How would you have used these the determinant of the in terms of like
Let me see why. So I think okay, we're a bit over time, so if you need to go, feel free to go. Okay, I'll have to think more about this and get back to you on Piazza. Because I can't think of, I don't know why it's not working now. But see, in the practice problems, they usually work out in the practice problems. Yep, thanks.
Thank you.
Yep, thanks. I also have surface integral stuff at the end that I didn't get to. Yeah.
so that's a question where it's solved. Can you, like, walk
Yeah,
through
this question works out. So like you're doing this triple integral of some function over this domain.
Yeah.
And so I choose u, v, and w.
So how did you choose those?
So I chose like the difficult terms. Like I see this, I don't want to deal with it. I chose that for u. I see a y over 2 and I chose that for v. And I see this and I chose that for w.
Wait, so you don't have to do what you did in the other.
In the other one, this was like a specific example where they wanted you to like use like this lower bound, upper bound thing to compare.
Right, so but you don't have to do this inequality thing where you solve for that and that becomes like y minus something. Like why is it just
Well, in this question, it'd be okay. You could like multiply by 2 on both sides, so you get like y is less than 2x minus y plus 1, and you subtract y. 0, 1. And you get 2x times 2. Oh, sorry, this should be 2. And you can divide by 2. So you still get the same thing. So you can start from your domain and simplify to get constants on both sides, and it'll still work out. So like this thing would be u.
Okay,
Thank you.
so then.
Yeah.
Will you post this?
Yeah, it is posted.
Yes.
Oh wait, I'll post. Yeah, this, yeah.
Wait, is this not posted?
This is like the notation version. So like without like these random notations, it is posted.
Oh, okay.
Yeah.
And then so then you have U, V, and W, and then what do you do?
Okay, so then we want to find the Jacobian matrix,
Mhm.
determinant. So I calculate that at 6.
Mm-hmm.
And so then when you find, you would also have to find the new coordinates. So let me actually go here. So it's all filled out nicely. You'd find the new bounds or the new limits. So x, we said, plug in what is x, plug in what is y, so that our bounds are now u from 2 numbers.
Okay.
V 2 numbers, W 2 numbers. When you use the formula, we rewrite our original function in u's and w's,
Mm-hmm.
multiplied by that derivative and du dv dw,
And then you just solve the interval.
and you solve. Get solved.
Okay, cool. Thank you.
Yep.
How do you get from this to that?
So you like multiply it out. So you have square root of this first term is rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta, right?
Mm-hmm.
Then you have this rho squared sine squared phi. If I factor it out, so I have this term times
Yeah.
cosine squared theta, right? That gives our
Mhm.
first term plus sine squared theta. Because this
Oh,
one
and that's one.
and this is 1. And so you have square root of that, which gives you phi rho sine phi.
Okay, perfect. Thank you so
Yep,
much.
you're welcome.
Mark, could you do number 10?
Number 10. Oh, yeah. That's a good question. That's a good one. Okay. Okay, so we want to choose like something for u and v. So I said like choose the difficult thing as our u and choose this as our v. So this has a bit to do with surface integrals, which I know you wanted to see. So I rewrote our like function of x and y as what we chose for our substitutions, and that's u and v. Now for surface integrals, the thing is, once we write this function, we want to take the derivative with respect to one of the terms. So the derivative of with respect to u is going to be partial of u with respect to x, partial of u with respect to y, which is 1, 1. We do the same thing with v, and we get 1, negative 1. Then you do the cross product, you get negative 2, and you take the length, you get 2. So for surface integrals, you always do this. Find a function, derivatives, cross product, length.
Was it length or absolute value?
Length. So this is
When is it absolute value? Because isn't it, when is it absolute value?
absolute value is like 1 line.
Like when, because like aren't some of them, you take the absolute value instead of the,
It might be like the absolute value of the length, maybe. But it should be the length. I hope. And you
or
get
isn't it, don't you do this when it's like it's only 2 vectors and you have to like make it a scalar?
because we only have 2 vectors and they're both 2D, it ends up being like, oh wait, maybe, wait, it might be like this is the cross product, you take the absolute value of it, but taking
Yeah, taking
the
away
length should
make it positive.
yeah also make it positive. And by the change of variables formula, we follow that du dv equals the derivative dx dy. This we just found is 2. So we have du dv equals 2 dx dy. And so dx dy equals this. So that's our new differential thing.
Yeah.
Okay. Now for the bounds, we drew this shape. Let's first look at the purple line. The purple line is y x equals 0.
Wait, I have a question.
Yeah.
So why did you need to, what did you do with this here?
Mm-hmm. This was used to find this.
Wait, so.
So we had to do all of this to find what is d sigma. D sigma is the surface integral. D sigma is this length, like this length, times du dv, or like your new variables. So like all this is the process of finding our surface integral.
Isn't this the process of just doing the normal change of variable? Like when did the change of variables?
So the change of variables, like I guess d sigma itself is dx dy. So like sigma equals dx. Oh, oh no. It's okay. So we have d sigma.
Yeah.
And we're changing variables to u and v.
Mm-hmm.
And so we found what
So if we didn't change variables, would d sigma be 2 dx dy?
2 dx dy. Yes,
Okay.
because we.
But then we changed variables, so didn't we have to find this matrix? Like how?
I think actually we might not be changing variables. I think it just might be the definition of like surface integrals. Actually, where is should be one of these. D sigma. Yeah, it's just the formula for, like, we're not changing any variables actually. So this is the formula for surface integral, and which is why we found the length or the absolute value of this cross product du dv. Okay, now for the bound, so we start with x equals 0. So x equals 0. So I used the, like what we chose for u and v.
But so that is changing variables.
Yes.
I think we only do the cross product when it's not a square matrix.
Not a square matrix. Oh, yeah, that might be.
Wait, I don't. Wait, what?
If it's not a square matrix, you need to do the cross product.
And then the magnitude of that to get like a number. But if it's like a square, you just take the determinant of it and then the absolute value. Which would also give you 2.
Mm-hmm.
Wait, so isn't that the process when you so I'm still confused about where you did change of variables. This is change of variables, that's not.
Let me think. So I think for surface integrals, you're kind of doing both at the same time. So like, okay, the process here, like we're doing like, we chose like something for v. It looks like we're changing, actually,
Because I get that.
yeah, I see what you're saying. because
Where's the process for doing the, because this right here is just, if this is just the surface
integral,
integral,
yes.
then where is the process where we also convert and do the determinant and all that stuff?
Oh, okay. Maybe this is why. So like for surface integral, it's not following the formula. This is just fu cross fv. So this is the surface integral thing.
Okay, but we also converted x to u and v. So where is the process where we adjust that?
When we're finding the bounds.
But don't we have to find the determinant and multiply that or divide that or whatever, like we did in the other question?
That's just this part already. So like doing this already accounted for. So first we change the surface area differential, and then we're switching the variables to u and v, and then by doing the surface integral, we've already changed to u and v.
Is that so? Every single surface integral is a change of variables question?
Yeah, essentially, it's like a specific type of a change of variables.
And could you say what you're saying again about how it's like when it's not a square matrix, you do this?
Because like the surface area ones, it's like when you have like, it's like this, where it's like X, Y, and Z, like you have 3 different like change of variables. It's not a square matrix, because you only have two inputs. So you can't take the determinant of it. So you need to do
Oh, okay.
the magnitude of the cross product.
Mhm.
Or if it's square, you just do the determinant and take the absolute value.
Yeah, that sounds right.
Okay, that makes sense.
Okay, then for our bound, so I first got u and v, but I want to rewrite it so that I have x equals something, u equals something, so that when we do substitutions, it helps. So I take this x equals 0. What was x? I found that x is u plus v over 2. So I set u plus v over 2 equals 0. You get u equals negative v. Then for the green line, this is y equals 0. I got that y is u minus v over 2. And I simplify, get u equals v. And you do the same thing for each of the lines. So the orange line, y equals x minus 1. You find that line, plug in y, plug in x, simplify, get v equals 1. Do the same thing for this red line here, get v equals 2. So now if you draw these 4 things in our UV plane, we get the purple line is this, green line is this, orange is between 1 and 2. So now our region is our highlighted region. Now that we have our bounds in our UV plane, our new plane, we can find the bounds normally. So normally we draw like a line in the increasing u direction. We enter at the purple, which is u equals negative v, exit at the green, which is u equals v. Then out of all possible lines, the smallest is the orange, which is 1, largest is the red, which is 2. And so this is your final integral. And you can solve this to see it's you get 3/4 v minus 1.
Can I take a
Thank
picture?
you.
Yeah.
I'll take 2 pictures.
Yeah.
Thank you.
Yep, you're welcome. Study hall tomorrow. Yeah.